Hello. So we will start off from where we had stopped in the previous lecture. So in the previous lecture, we had stopped at relaxation oscillators and we had seen what relaxation oscillations look like. So those oscillations, as we had seen in the previous class, have two time scales, a shorter time scale and a longer time scale. And different parts of the oscillator moves differently. There are certain portions of the oscillation which occur much more slowly than the others. It's as if those portions which occur slowly have to where the oscillator has to overcome a greater deal of stress. And when the stress is released, then the slow part goes away and the fast part of the oscillation comes into the picture. So I'll just recap what we had done in the previous lecture. So we had the equation of the Van der Waals oscillator over here. This is a very famous nonlinear oscillator, as I mentioned earlier. And we solve this equation in the limit where mu, that is the coefficient of the nonlinear term, is much, much greater than 1. So this is a strongly nonlinear system. Okay. So then what we do is that we consider only this part of the system, and we can write it in the form of this particular equation that ddt of this thing is equal to 0, provided that the system is a strongly nonlinear system, right? By neglecting out the other x part. And then we define a quantity f, which is x cubed by 3 minus x. And then ddt of x dot plus mu f becomes equal to 0. Then we substitute this back into the original equation. And once we do that, we get an equation like this. Then we assume omega to be of this form x dot plus mu into f. And then omega dot is in that case minus x. From this, we get an equation for x dot and w dot. And then we make the further change of variable that y is equal to w by mu, which turns out to be x dot plus mu f by mu. And then we arrive at the final form of the coupled first order systems, which we then analyze with the methods that we have already learned before. So we can see from these equations that there are two null claims of the system, that is x dot equal to 0 and y dot equal to 0. So the x dot equal to 0 null claim, or the x null claim, basically corresponds to y equal to fx, or it corresponds to the line y equal to x cubed by 3 minus x, which is this cubic line which you see in the phase diagram. And the y null claim, which is y dot equal to 0, basically corresponds to the y-axis. So along the x null plane, the flow is vertical, and along the y null plane, the flow is horizontal. And since mu is very large, away from these null planes, the flow is almost horizontal because y minus fx becomes finite, and multiplying that by mu makes x dot very large. On the other hand, because mu is large, y dot is very small. Therefore, away from these null planes, the flow is always horizontal and parallel to the x-axis. And close to the null plane, the trajectory creeps along the null plane until it reaches either of the extremum. Okay, and this creeping happens because the downward velocity tries to push it away from the null plane, and as it moves away from it, there is a horizontal velocity which brings it closer to the null plane. So the fast parts of the oscillation are the horizontal portions over here. So these are the fast parts, and this is again the fast part of the oscillation. And when it goes along the null plane, then it encounters the slower part of the oscillations. And so if we try to draw a time series of the variable x as a function of t, then you see you get these parts alternating. So these are the slow parts where variable x changes minutely with respect to t. And when x undergoes drastic changes with respect to t, that basically represents the horizontal arms. So these vertical portions in the time series are the fast parts of the oscillation. Okay, so what this analysis shows us is that there are two widely separated time scales. So this is an underlying feature of relaxation oscillations. There are multiple widely separated time scales. For example, the slower part of the oscillations, they happen over a time scale tau, which is of the order of mu, and the faster ones, they happen on the time scale of the order of mu inverse. Okay, as you can see, this time scale is much smaller than this one. Okay, so now that is understood. The next thing that we try to extract from this system is what is the time period of one oscillation of this limit cycle. So the question is, what is T? Okay, just for the sake of convenience, I will open another new mode. So what is the time period of the oscillation? So as you saw, the limit cycle looked like that. There was this line over here, and if you had a trajectory starting from here, it will go like that. Okay, so basically the time period of oscillation, if I denote this point as A, C, and D, then the total time period of oscillation is basically given by the time taken to go from A to B, from B to C, to D, and D to A. Now, in comparison to this one and this one, which are the slow time scales, this one and this one is much smaller. And moreover, from the symmetry of the problem, we can assume this one and this one to be roughly equal. So then the total time period, it roughly becomes 2 times PVC. Okay. Or in other words, it is 2 times. All right. Now, as it goes from point B to point C, you can see that it travels along this null plane, y equal to fx. Okay. So how do we write dt in terms of the variable x in that case? We know that dy dt is almost equal to x into x dt, right? Because y is almost equal to fx along the path from B to C. So then this becomes okay. But we had seen from the equation that this is nothing but minus x by mu. So therefore, we have dt is equal to mu into minus mu into x square minus 1 by x into dx. So then we can substitute this into the earlier equation and obtain 2 times x at c, x at b. So the next question is to find out the limits of the integral x at b and x at c. So we can look at this diagram. So x at c is nothing but the value of x at the minima of the y null x null plane y equal to fx, and x at b is nothing but the value of x corresponding to the value of y at which the maxima is reached. Okay, so we had the equation for the null plane to be y equal to x squared by 3 minus x, and if you f dash x is equal to um, x squared minus 1, so this is 0 at the extremum. So this means x equal to plus minus 1. And since we are looking at the positive branch, we have x equal to 1. Okay. Now corresponding to x equal to minus 1, what is the value of fx? Because we want to find the value of the maxima of the function. F at x equal to minus 1 is nothing but minus 1 by 3 plus 1, which is 2 by 3. And corresponding to 2 by 3, what is the value of x? X is 3 by 3 minus x equal to 2 by 3. So now we have to solve this cubic equation. All right, you will see that a solution to this cubic equation, positive solution to the cubic equation is x equal to 2. And then this corresponds to xp. So therefore, you can write this as 2 mu integral x was equal to what? X was 2. Okay, so this is nothing but 2 mu into log x minus 6 by 2 to the limits 1 and 2. Actually, there has been a mistake in the limit. So the flow is going from B to C. So this should be here T and TC. Okay, right. So it should be C. So this should be 1, this should be 2, 1 and 2. And finally, we get 3 minus 2 and 2. So in this way, we can find out the time scale of oscillation of the limit cycle. So as we had seen before, this is of the order of mu, as we had expected. So one thing to note in this problem is that the slow and the fast time scale they occurred one after the other in series. Okay. Now what happens if they don't occur sequentially, but they operate concurrently? That means both of the timescales are overlapped with each other and they occur simultaneously. So that will bring us to the case of weakly nonlinear oscillators. So when we had done this relaxation oscillations, we had seen that the system under consideration had a large value of the nonlinear term. The nonlinear term was assumed to be much more dominant than the linear one. Here we do the opposite. Here we assume that the nonlinearity is a weak one. So a prototypical example of a weakly nonlinear oscillator is a system like this, plus epsilon h as a function of x and x dot equal to 0, where we assume that epsilon is a very small positive quantity. So a classic example of the weakly nonlinear oscillator is, for example, the Van der Pol oscillator, where we can consider mu to be much less than 1. Or we can also have an oscillator which looks like this. This is called the Duffing oscillator. This is also a typical nonlinear oscillator that has much applications in nonlinear circuits and neural networks and so on and so forth. Neuronal networks. Okay, so when epsilon is very small, let us consider the case of the Van der Pol oscillator for simplicity. So the Van der Pol oscillator, if you recall, it is written like this. So when epsilon is a very small quantity, then what happens is that these oscillations, they gradually build up from the origin. The origin is an unstable fixed point. They gradually build up from the origin and appear to approach a stable limit cycle like this. Okay. So there is a limit cycle over here. The oscillations gradually build up and approach this limit cycle. So one way of treating these systems which have a small nonlinearity is in the form of a perturbation theory. But we will now show that the perturbation theory actually ends up failing when even if there is a small nonlinearity in the system. So let us see how it fails first. So our first approach to solving this problem analytically is to use perturbation theory. So the basic assumption of a perturbation theory is that the solution of our equation, that means xt as a function of t and epsilon, can be expanded in a series of the following form. So it can be expanded in a series of and higher order terms. So basically it can be expanded in a series of the small parameter, which here is epsilon. Okay. So consider the weakly damped nonlinear oscillator, which looks like this. With the initial condition that x at time t equal to 0 is 0 and x dot at t equal to 0 is equal to 1. Okay. Now, an exact solution for this system is like this. 1 minus epsilon square minus half e to the power minus epsilon t into sine of 1 minus epsilon square to the power half into t. So this is the exact solution of the system. And you see the exact solution basically is of the form of a sine wave with a decaying amplitude. And the amplitude decays exponentially with time. So this is t and this is x. Now we have to see whether the solution that we get from the perturbation theory agrees with the exact solution or not. So this was our perturbation solution. Let us call this equation 1. And then dx dt is basically then x0 dot plus epsilon x1 dot plus epsilon square x2 dot and so on. And similarly, we can get d2x dt as well. So if you look at this system of ours, equation 2, then if you substitute 1 into 2, what you get is square of x0 plus epsilon x1 plus epsilon square x2 plus 2 epsilon x0 plus epsilon x1 and so on plus x0 plus epsilon x1 plus epsilon square x2 so on equal to 0. So what we now do is that we separate the powers of epsilon from 1 by 1 and we only include the terms which are of the order of epsilon or lower. So we neglect all terms which are of the order of epsilon square and higher. So then rearranging the terms in this equation gives us x double dot plus x naught. So this is the 0th power of epsilon plus epsilon into x1 double dot plus 2x0 plus x1 plus terms of the order of epsilon square equal to 0. So now we try to find the solution order by order. So the order 1 term, if you try to match the orders of the left hand side and the right hand side, you see that basically you match the coefficient of epsilon from the two sides of the equation. You see this is 0 and order epsilon basically gives me x1 double dot 2x0 plus x1 equal to 0. So I call this equation 3 and this one equation 4. So we ignored the order epsilon square and higher terms. So now at t equal to 0, we had x equal to 0, right? So that basically means that x0 plus epsilon x1 0 started equal to 0. And by using a similar argument that the derivative of, of at the initial point, that is x dot plus 1, we obtain that x0 dot plus epsilon x1 dot time equal to 0 equal to 1. So now since this particular equation, the initial condition and this equation, this holds for all values of epsilon, regardless of what epsilon is. This basically implies that x0 at t equal to 0 is 0 and x1 at t equal to 0 is also 0. And the second equation, this one, this implies that x0 at 1 and x1 dot, because this is supposed to hold for all values of epsilon. So once we have these equations, we can solve 3 and 4. So solving equation 3, for example, gives me x0 dot equal to some amplitude a into sine of t. And since at t equal to 0, x dot equal x0 is 0 and x0 dot is equal to 1, this amplitude is equal to 1. So this is equal to sine t. So let us solve this equation 5. Now if we put x0 t equal to sine t into equation 4, then we get x1 double dot plus x1 equal to minus 2 sine t. So you see this is an undamped harmonic oscillator with a sinusoidal periodic force. Sorry, would have been x0 dot. And therefore, this should not be sine t, rather this should be cos of t. Call this equation 6. So the right hand side of equation 6 is basically a resonant forcing. And given the initial condition that x1 at t equal to 0 is 0 and x1 dot is equal to 0, a solution of this equation turns out to be of the form that right. So the solution of this equation, this turns out to be of the form x1 minus t into sine of t. This is equation 7. So you see that as t goes to infinity, this solution goes to minus infinity, right? So according to perturbation theory, then the whole solution x of t should be of the form x0 plus terms, which should be um, so you see what happens is that as t goes to infinity, x of t goes to minus infinity. Right, so the solution blows up in the finite time and it does not converge to this solution which we expect. So if you try to plot a graph of the solution, the graph of the solution would look like this. So when the t is small and epsilon is small, then it will sort of follow this oscillation. The amplitude will decrease like this, and beyond a certain time, the amplitude will rise, and the solution will go to infinity like that. So this is the wrong solution because it does not match with what we had obtained from the original solution. Now, why is this so? This is because you see that x of t is actually a series expansion. And what we had done was that we had only expanded up to the first order term in epsilon. So the first order expansion is valid only up to a certain time scale. Beyond that, what happens is that the epsilon squared terms, they become important in the solution and we need to include them as well. So we have to go to very high orders to finally get this series to converge. And most of the time, it is a very difficult task to do. Now, the main reason that the solution had blown up was that there are two time scales in the system if you look at. So if you look at the original solution, it had the form of the power minus epsilon t plus a into sine of 1 minus epsilon squared to the power of into t. So there are two time scales over here. One is the oscillation period of the sine wave, and the other is the modulation of the amplitude, which has an exponential decay. So out of these two time scales, this one is the fast time scale, right? Because the sine function oscillates, completes one oscillation in one period. On the other hand, since epsilon is a small quantity, this one is a slow time scale. And unlike the previous problem, now you have both the fast and slow time scales acting simultaneously. So now we need a better method to get an analytic approximation of the solution. So this brings us to our second approach, which is called the method of two timing. So two timing is a very intuitive method that can give nice approximations in systems which have two such very disparate timescales, and both of these timescales act simultaneously. So let us define the two timescales as t and epsilon t. So as you can see, since epsilon is a small positive quantity, this is the fast timescale and this is the slow timescale. And we assume that these two variables, tau and capital tau, are independent of each other. Okay, so we'll treat them as independent variables. So now we turn to applying this method to our solutions. So the full solution, again, we expand it in powers of epsilon. In this case, the variables x0, x1, and so forth are now functions of tau and t. As order epsilon square terms. So then the time derivative of the variable x dot, x that is x dot is basically dx by dt. So using chain rule, we can write that as del x by del tau, this is partial derivative, plus so this is nothing but so this is what the first derivative would now look like. or we can also write it in a shorthand notation like this. Similarly, we can write the second derivative as well using the chain rule, and that turns out to be x double dot dx dot dt. So if you substitute x dot from equation 2 into this thing, you can write the expression for x double dot. Okay, so now let us take a look at the original equation which we had. So the equation which we had was before that, let us just write down what happens after we substitute 1 into 2. So if you substitute the series expansion of x into this, then you basically end up getting x0 plus epsilon into and similarly, if you substitute that into equation 3, then you get now what we do is that we apply this method to the earlier problem that we were trying to solve. So now if I replace the equation 5, equation 4, and equation 1 into this model over here, and then I collect the powers of epsilon, then what I get is that the order 1 term is like the order epsilon term. This will now scale as so this I denote as equation 6 and equation 7. So now we have to solve 6 and 7 subject to the initial conditions which we had earlier, that is equal to 0 and x dot 0 equal to 1. So substituting this into equation, so the solution of equation 6, it basically turns out to be x not equal to a sine t or sine tau plus cos tau. But now here is the interesting part, because now we have considered these partial derivatives of, we have considered the variables as tau, as tau and t, and not capital T and not the small t variable. We have basically assumed that the first time scale tau, so the quantities which depend on the slower time scale, we are basically regarding them as constants over the fast time scales. Sorry, the quantities which depend, the quantities which depend on the slow time scale are regarded as constants on the fast time scale. For example, if you think back about the exponentially varying amplitude of the pendulum, then the exponential decay in the amplitude takes place over a lot of oscillations. But if you look at a given oscillation period, the amplitude roughly stays constant over there. So that is the basic idea over here, that the variables which depend upon the slow time scale are roughly regarded as constants on the fast time scales. So here A and B, which might seem to be constants, are not actually constant, but they are functions of the slow time scale. So actually A is function of slow time scale AT, and B is a function of capital T over here. So to determine these functions A and B, what we do is that we must go to the next order in epsilon. Okay, so therefore we look at equation 7. So putting this, we call this equation 8. If we substitute 8 into 7, what we get is as follows. Where A prime is nothing but dA by dt. So primes denote differentiation with respect to capital T. Now you see that the right hand side has two resonant terms, and including them in the solution would give us exponentially blowing solutions like we had seen earlier. So these are secular terms and we need to get rid of them. So what we do is that we have to set the coefficients of these secular terms to be equal to 0. So we have A plus A prime equal to 0 and B plus B prime equal to 0. So these equations, they give me solutions of the form that A of t is equal to A0 b to the power minus t, and B of t is 0 b to the power minus t. So in this way, we are able to fish out the amplitudes as functions of the time. Now we look back at the initial conditions, that x at t equal to 0 is 0 and x dot at t equal to 0 is 1. And using these initial conditions, we are able to find out the values of A at t equal to 0 and B at t equal to 0. Okay, so if you do that, then it turns out that 0, 0 and t0 is equal to 1. Therefore, we finally have the overall solution to be that x0 is equal to A sine tau, which is e to the power minus t into sine tau. So therefore, the overall solution x, which is nothing but so on and so forth, we again have this x1 term going to 0 because it has to satisfy the required initial condition. So the initial condition was that um, so the initial condition states that right. So because we had the initial condition that x equal to 0, this implies that x10 should be equal to 0, and we also had the initial condition that x dot 0 is equal to 1, which also basically implies that this is independent of epsilon, so x1 dot is equal to 0. And since the right hand side of the x1 dot term is equal to 0 and its initial value and initial derivative are both 0, so this basically implies that x1 at any time t is equal to 0. So therefore, this term cancels out, and we finally have the solution to be minus t sin tau plus order epsilon square, which is equal to e to the power minus epsilon t sin t plus order epsilon square. So you see that the approximate solution, which is predicted by the two timing method up to first order, is very close to the exact solution that we get. Okay, and this is a very surprising thing because nobody knows why two timing works. It just ends up working well enough. So similarly, one can also apply this two timing methods to other complicated systems like Van der Waals oscillators and so on, where the nonlinear term is where the nonlinearity is relatively much bigger than the other terms in the system. Okay. So with that, we conclude this part, and then we would next move on to bifurcations in 2D systems. So we'll start off with this after 5 minutes. Hello. So coming back. So next we start off with bifurcations in 2D systems. So bifurcations in 2D are quite similar to what we saw for 1D systems as well. So you will see that here we also have the typical bifurcations which we had for 1D. That means saddle node bifurcation, transcritical, and both the supercritical and subcritical bifurcations. But here these bifurcations can have various different kinds of implications and can generate more rich or complex behavior than in 1D. So let us start off with the simplest one, that is a saddle node bifurcation in a 2D system. So a typical example of a two-dimensional system showing saddle node bifurcation is this: y dot equal to minus y. So one thing that you will notice is that this is a system of uncoupled equations. The flow in y is in the y direction, and the flow along the x-axis is always in the x direction. Okay, so what do the parameters of the system? What do the phase portraits look like? So the fixed points of the system are basically y equal to 0 and x can be equal to plus minus mu. So if this is my x-axis, then this is one fixed point and this is another fixed point. And if you do the stability analysis, you will see that this one is a stable fixed point and this is an unstable fixed point. And the flow towards a stable fixed point is like this. And this one is a saddle fixed point. So the flow is like this. And all the trajectories which are here, they approach the stable fixed point like that. Now, if you set mu equal to 0, then what happens is that these two fixed points, they collide with each other at the origin. And then it gives us an semi-stable fixed point. So it is stable from this direction and the flow converges towards it along the y-axis and it looks like this. If you have a flow over here, it will go like that. And finally, when mu becomes negative, then the two fixed points collide and disappear entirely. And then you have a flow going to minus infinity like that. So this is the x-axis. So there is a saddle node bifurcation by which the two fixed points disappear. So this is a very special case where the two equations were uncoupled. It may also have the two equations to be coupled as well. So what happens is that the saddle node bifurcation occurs due to the motion of one null line over the other. So suppose you have a system where this is my x null line, x not equal to 0, and this is my y null line, where y dot equal to 0. So basically the intersections of the null lines are where the both x dot and y dot are simultaneously equal to 0, and therefore they correspond to the fixed points. So this is one fixed point and this is another fixed point. Now suppose this fixed point is a saddle fixed point and the flow is like this over here. Or in other words, suppose that this is a repeller and this is an attractor. The flow is towards this fixed point and away from that fixed point. And now as one changes the parameters, what can happen is that this null plane can move in this direction. And then you have a situation where these two fixed points, they approach each other along this null plane, and then they collide with each other and disappear and give rise to a saddle node bifurcation. Okay. So in this next example that we do, we see an example of such a generic saddle node bifurcation. So the system that we consider is like this. And so this is a model for a genetic control system. Okay, I won't go into the details of the model because mainly we are interested in studying how the bifurcation looks like. So we assume the parameters. Yeah. So we assume the parameters A and B to be greater than 0. So the first thing that we need to do is find the fixed points of the system. And as I mentioned earlier, that the fixed points are basically the points where the null planes intersect. So the null planes are given by x dot equal to 0, which is so the null planes are basically given with equal y equal to x. This is the x dot equal to 0 null plane, and the other null plane is given by y equal to x squared by 1 plus x squared, or in other words, this is y is equal to this thing. This is the y dot equal to 0 null plane. So since we are considered, uh, we're only concerned with the positive definite values of x, the null planes look like this. So this is y dot equal to 0, and this is x dot equal to 0. So as you can see in this diagram, there are three fixed points of the system. And the fixed points are given by the intersection of the null planes. So that basically implies that Ax should be equal to x squared by 1 plus x squared into b. So one point of intersection is x equal to 0, which implies that um, y equal to 0. So 0, 0 is a fixed point, and the other positions of intersection are given by the quadratic equation that x equal to b into 1 plus x squared. So the solutions to this equation will give me the other two fixed points, right? So the solutions to this equation are basically given by x star equal to so these fixed points vanish when 1 minus 4 squared b squared becomes less than 0. So when this happens, then what happens is that this x nullify intersects with the y nullify only at the origin, and there is only one fixed point. And then the two fixed points are just about one when this quantity becomes greater than 0, or the position of the birth of fixed points is that for the existence of fixed points we must have greater than 0, which implies that AB should be less than 1. Okay. So we can define a critical value of the parameter A as 1 by 2b. So let us assume b to be fixed and see what happens as we vary a. So when a is less than a critical, that is a is less than 1 by 2b, then you have all three fixed points, and when a exceeds a critical, then there is only one fixed point, that is at the origin. Okay. So a saddle node bifurcation occurs when a is equal to AC. And what does the flow look like? So a physical way of interpreting what the flow looks like is to study the properties of the null themselves. So along the x null plane, that is x dot equal to 0 null plane, the flow is vertical. So here the it's in this direction, here it is in this direction, and here it is in this direction. Similarly, over here the flow is in this direction, flow here is in this direction, and here it is in this direction. All right. So this basically implies that the flow will be away from this fixed point sort of in this direction, and it will try to approach the fixed point from this direction. So this basically implies that this one will be a saddle fixed point. On the other hand, it appears that the flow tries to approach this fixed point from all directions, and therefore this one is the stable fixed point. Okay, so we see that when the saddle node bifurcation occurs, there is a stable fixed point and a saddle node and the saddle fixed point, which is spawned. Now we can also calculate the Jacobian matrix, and we can get a similar result, which will ultimately show that this one ends up being a saddle stable node and this one is a saddle point. And once we know the natures of these fixed points, we can also draw the base portrait, which will look like this. So you have the saddle over here, whose unstable directions point in this way and stable directions point in this way. Similarly, you have a stable node over here, and this is approached from all directions. So in this way, we can actually calculate the nature of the from the nature of the fixed points, we can also calculate the phase portraits. Now we can also similarly define the transcritical pitchfork bifurcation and other types of bifurcations that may occur in this case. So the transcritical pitchfork bifurcation can be defined using this parametric equation like we had in 1D. And then one can also define the supercritical and similarly the subcritical pitchfork bifurcations by similarly using the prototypical form from the x-axis while using y dot of this particular form. Okay. So now what we do is that we move to a special kind of bifurcation which occurs only in 2 and higher dimensions, which is called the half bifurcation. Now, half bifurcation basically talks about the bifurcation of a limit cycle. It is basically similar to a pitchfork bifurcation. Only thing is that it is a pitchfork bifurcation that occurs in the plane polar coordinates. And you will see that when you have a pitchfork bifurcation occurring in the plane polar coordinates, then basically you can have like if you remember, if you think about the pitchfork bifurcations that we had seen earlier, we had one fixed point which was a stable one, and then it gave rise to two unstable and one stable fixed points. Sorry, one fixed point was unstable, and then it changes its stability, becomes stable, and there are two more unstable fixed points that come from, so and so forth. So basically, this was the form of pitchfork bifurcations which we had seen before. And here, if you consider the unstable and stable fixed points in the radial coordinate r, and then you have a theta coordinate, which basically represents the oscillations of the system, then you will see that there are bifurcations of the limit cycle by which a stable and unstable limit cycle can form if you change the parameters. So, and yeah, so that's what we'll see right now. So there can be two types of bifurcation, as I was saying. One is critical, and the other is a subcritical one. So the typical equation for a supercritical half bifurcation is given by q minus rq theta not equal to omega plus 3r squared. Now, if you assume the parameter p and omega to be positive, then theta is always positive and it never becomes zero because r cannot be imaginary. So this basically implies that the solution will keep on oscillating in a given particular direction. And now let us see what happens if you change the parameter. So mu is the variable parameter over here. Now let us take one look at the 1D system in the radial coordinates. So this is similar to pitchfork bifurcation in R itself, as I was mentioning before. So if you look at the R dot phase plane and you choose that is less than zero, then you have something like this. Sorry. So the flow flows towards a stable fixed point at the origin. And when mu just becomes greater than zero, You have something like this. So there is a pitchfork bifurcation in R. And when there is a pitchfork bifurcation in R, that translates into a Hopf bifurcation for the limit cycle. So what does this imply for our 2D system? So mu equal to 0. This basically means that R equal to 0 is a stable fixed point. So this means that the origin is a stable fixed point and all the trajectories, they come from far and spiral in towards the origin like this. So there are trajectories which come from here and go in like that, and also from here. Okay. So this is the case that happens when mu is less than 0. Now, when mu exceeds 0, now there are two fixed points, okay, at plus r and minus r. Now, since r is the radial coordinate, we only consider the positive part. So basically, what happens is that when mu just about exceeds 0, then the fixed point at r equal to 0 loses its stability, it becomes unstable, and the new fixed point is born at r equal to say r star. So what does this translate into? This means that the stable spiral, it undergoes a bifurcation and becomes unstable when mu just exceeds 0, and the stable limit cycle is born whose radius is equal to r star. So here you had the unstable fixed point. What happens is that the trajectory spiral outwards from this and it approaches the stable limit cycle and then oscillates around it like that. Similarly, trajectories which come from far, they come around like this and then they begin to oscillate about this limit cycle and then go around like this in this circle. Okay, so there is a stable limit cycle which forms over here. So this was an example of a supercritical pitchfork bifurcation where the origin, which was initially stable, loses its stability and gives rise to a stable limit cycle. So if you, instead of the plane polar coordinates, if we go back to the Cartesian coordinates and try to analyze the system, then you will see that if you calculate the Jacobian of the system, it gives um, eigenvalues which have a negative real part when mu is complex conjugate eigenvalues, which have negative real parts when mu is less than 0 at the origin. But then the Jacobian at the fixed point of the origin has eigenvalues with positive real parts when mu exceeds 0. Okay. Now, similarly, one can have a case of this subcritical Hopf bifurcation. So this was supercritical. Now, when the bifurcation is subcritical, then it has this particular form that r dot equal to mu r plus r cube minus r to the power 5. So, as in the 1D thing, here the r cube term becomes the destabilizing term, and there is a higher order stabilizing term of the form of r to the power 5. So if we try to analyze the dynamics in the parameter space of mu, then what you see is that when mu is less than 0, there can be a situation, I mean, when mu is greater than a critical value, but less than 0, then one can have the following situation where r dot plane, there can be 5 fixed points. Yeah. So if you look at the stability, so it's a stable one, and The origin is stable, but there are two unstable fixed points over here. And when mu exceeds 0, then what happens is that there is only a origin becomes unstable, and there exists only a single stable fixed point like this. Origin is unstable, and this becomes a stable fixed point. Okay. So since we are only concerned with positive values of R, we look at only this half of the phase diagram of R. All right. And when mu is less than the critical value of mu, then the origin is the only stable fixed point, and the unstable fixed points and the other fixed points don't exist. Okay. So how does this translate into the two-dimensional system, the Cartesian coordinates? So what basically this implies is that there is an unstable limit cycle that surrounds the fixed point at the origin. Just 1 minute. So there is an unstable limit cycle which surrounds the fixed point at the origin. And the fixed point of the origin is a stable fixed point. And there is a larger stable limit cycle which surrounds the unstable limit cycle. So what happens is that the trajectories which starts from just inwards of this, they spiral in towards the origin, while the trajectories which just start outside of this, they spiral towards the larger limit cycle. Okay. And this basically translates to our earlier situation where there is a stable limit cycle outwards and the origin is unstable. So all trajectories would approach it from everywhere. So this is a case of a subcritical half bifurcation. And as we had seen for the subcritical pitchfork case, there is a hysteresis. That means just merely bringing mu back to 0 from a positive value will not give me will not stop the large amplitude oscillations of the limit cycle because they will continue to persist. Mu has to be brought down actually below this critical value for the large amplitude oscillations to stop. Okay. So that covers the details of Hopf bifurcation, which is a new type of bifurcation that can occur in a two-dimensional system. So we will, in the next lecture, we will take a look at a few problems on bifurcations in two-dimensional flows, and then finally move ahead to three-dimensional systems, which can show chaotic behavior. So that's it for today.